This is part 2 of my review of lecture 17, orthogonal matrices in Gram-Smith. So let's touch upon lightly on the previous topic, which is the Q being rectangular and Q being square. So this one, I found that in the book it is called matrix with orthonormal columns, while the one with the square, it is called the orthogonal matrix. So the orthogonal matrix, if I am correct, it implies also the matrix being square and has orthonormal vectors. So you can read it this page, 2 pages, and where you can find more information about those two. And remember about some really important properties about them. So in this case, in the case of rectangular, the Q transpose Q is identity, while Q transpose is not identity. So this one only gives you the left inverse, so you have to be careful. And while this one, it has really nice properties where the Q transpose Q equal to Q transpose and equal to identity. So in this case, the Q transpose itself equal to the Q inverse, and it gives us both left inverse and the right inverse. So let's move on to our third point, 3. So we want to talk about why Q is being useful. And let's see, let's change all the A into Q. So let's bring up all the 3 favorite equations from the previous review, which is this one and this one and this one, about the projection. And let's convert the A into Q, and let's see what we got. And let's imagine here, so we have Q transpose Q x hat equal Q transpose B. So what will that left us is just the identity times x hat, which is just x hat equal to Q transpose B. And this one simply translates to the projection equal Q x hat. And the projection matrix gives us, because this will be QQ, so A transpose. Because A transpose A is Q transpose Q, and as you can see, the inverse, it's the identity, and identity inverse is just identity, so this will be A transpose. Okay, and another thing that is quite interesting is, in this case, if we expand this one, it will give us Q, and x hat is Q transpose B. And let's focus on this one. Let's move on into this part of the page. Let's figure out what is Q transpose B first. So this is simply just the dot product between each column of Q, because, well, let's say Q1, Q2, Qn, and then there's a B here, B1, B2, so forth. And the Q transpose is just the dot product between all of them, one by one. So Q1 dot product with this B, Q2 dot product with this B, and so on. So you will left with a scalar value on each component. So let me have this like Q transpose B, Q2 transpose B, and Qn transpose B. Now this is just a scalar value. And then let's do the other one. So let's do Q, and let's delete this one first. Okay. And what if we multiply the Q here? Again, like only the column vector Qn. So this is just acting like the combination of the columns, right? So in the end, we will have the Q1 transpose B plus Q2 transpose B, and so on and so forth. So this is quite interesting to see, and it is also mentioned in the book, so that's why I want to mention this here as well. So this will leave us with matrix of m times 1, because this is m times n, and this is already n times 1. Correct. Okay, so let's move on to this important case that will happen here. So I will delete this one first. So let's not forget that there is also a possibility, an important case, where the Q is an orthogonal matrix, which is the square matrix. So what happened here is that the Q, I'm sorry, this is terrible. So this one should be not AA transpose, but the QQ transpose. Okay, sorry. So yeah, let's move on. So in this case, the QQ transpose is also identity because it's squared. Square matrix. Okay, so the P is the identity itself. And what will this give us is the fact that the projection matrix of B is equal to B, because we're trying to project B with some matrix of identity, which is something that will not change B at all. In fact, if you convert this one into identity, you will also have inverse of B. So P equals B. Now intuitively this is really makes sense. So let's say we are in the R3. So let's say this is like X, Y, Z. Okay, I'm sorry, this should be Z right there. And let's say this is our vector B that fills up the whole space. So B is in the R3 as well. And we want to project B into something, into the whole space. We want to project B into the whole space, not into some subspaces. We want to project B into the whole space because the Q itself being the square, and well, maybe look like this or whatever, but it looks like the Q is independent and they stretch all the dimension, and it was really a good matrix. So we want to project B into the whole space. So what we will get? Well, we got the B itself. It doesn't move. It's just the best projections of B that we got into the whole space. So intuitively that will also make sense. So that's it about the point number 3.